And you can actually find that online if you are interested. It's gotten a little long in the tooth in terms of lots of people using it. Our 3D collectome is something called spatial.io, something we picked up on about a year ago. That same idea where a collectome can let you mash up a number of visual representations. And by the way, you could put a Sketchfab model into one of those components of the collectome. But why not take it a step further? Let's make it a virtual world. And this is what Spatial does. It's a game engine. It's, to do online gaming and social networking. Some of you probably might remember Second Life from way back. So that's coming back around again. It's not as cheesy. You don't have to buy real estate. There's still some mod characters out there, but people generally don't worry or mess with the these environments that we set up for visualization. But you can go and try out some of these on your own. So please download the slide set and check them out. These are fun because they also bring in some generative AI to show the accessibility of both collectomes and spatial.io. The SciViz course I'll teach it again this fall. We had students, master's students, no PhD students, actually did by far a great job of they were doing visualizations in ParaView. They can export these models to Sketchfab, and then from Sketchfab, they also actually made videos, and they put those up in YouTube and stuff. And so this is Jay Esch's and his team's things. We could critique the visualizations. Are these the best visualizations? It was from one of the IEEE. Hey, great, got some visitors here. So we think this is what's going to certainly make it much more interesting, because it can then be a collaborative type of experience. So again, here they did a vector field visualization. By the way, I should kind of take a first-person view here. Also works well in a headset. So again, honestly, I love virtual reality, but I probably wouldn't have my staff or myself spend much time on it if we had to do a bunch of work to get it in there. But if we're putting it online and we can get the VR like literally for free, then absolutely, then it's cool. And then it helps make your work that much more memorable. And this one last one we actually were working with environmental scientists. Again, they do a great job of conveying information about climate change. It's called the Environmental Resilience Institute at Indiana. But they can't really compel people to change their actions. Or we say they do a great job of educating the mind, but they don't educate the heart. Is this the right answer? Not exactly, but I think it's closer. This has a way to get people to engage. If you walk through this world, you can see we, again, use generative AI to create lots of scenarios that were plausible for a location in the U.S. Midwest. So all kinds of things there. So again, it's going beyond, it's taking your science and getting it out there so that people will interact with it. We think that's really important. A few other technical things that I think are important. We've talked about ParaView and the GUI. One thing I realized I didn't put in any of these slides, and Ali got me thinking again, how you get your data into ParaView. Let me just say a thing or two Of course, you can take your data, you can write a script to convert it into one of the ParaView supported file formats, and there's like 100 of them. And if your university has money, you can pay ParaView to support, or pay Kitware to write a data importer for it. You can also write your own if you want to. Or you can actually just write a script to convert it into, say, a VTI file or a VTP file or a VTS file structured. You can also do something like CSV files. Still very popular. People got things written out there. You can read that in. We've seen that spreadsheet view. What ParaView doesn't understand is maybe 3 of those columns are the X, Y, and Z location of something, but there is a filter that actually will do table to points, and then you have to specify which of the columns in your table is the X coordinate, Y coordinate, and Z coordinate, and then it will pull those out and put them together. And then the remaining values it will make as scalar values, or if you want to turn them into vectors. So you have to do a little bit of work because it doesn't understand which ones are coordinates, which ones are colors, which ones are scalars, which ones are vectors. But that is all possible. And once you've done that, then you can use the data export feature to save it out as an appropriate VTK format. So it is very possible to use ParaView as a way to transform your data. And that obviously only needs to be done once, and then your data is in a good format. But you can do a lot of great things with the GUI in ParaView, but you can also bring Python you can use Python in 2 major ways. You can use Python to help do more things in the GUI that aren't natural through pushing buttons and stuff. And then you can turn it around and you can run ParaView in a headless state, and you can run ParaView from the Python command line. I think I say that. So again, some of these I borrowed from the Cornell Virtual Workshop, and just going through these, there's a thing called a calculator we blew right past. But sometimes, again, you get a X, Y, and Z value that are representing a vector, or an I, J, and K value. How do you actually turn that into a vector type? That's where ParaView has something called a calculator. And it looks like this thing on the left, and it looks like the old school scientific calculator. And that can work for a lot of things. You can even do some vector functions. But sometimes you need to dip down into a NumPy or SciPy library. Like this one actually is computing the area of each of the triangles that makes up that sphere. So you can put a NumPy or SciPy expression in there. So this is called the Python calculator. Okay, we talked about filters that take one type of data and create another, do something to it, change its representation, do something that's a filter. A source has no input, so when we want to create a sphere, a cone, or something. And ParaView lets us create both of these with Python, and you can see, now this requires you to understand VTK a little bit, because basically you're doing VTK and ParaView commands and Python. But if you do understand those things, you can put those in there, and then you can still have all of the benefits of the GUI there. So you can make sources, or you can make your own types of filters. And then lastly, you can have the GUI going, and you can pull up what they call the Python shell, and you can talk straight to the rendering engine. So this is a really simple example. This is how you would actually create a sphere, but you can actually see it, and when you type these commands into the shell, you will actually see the pipeline browser. These things will get added to it. It's also the case that you can do things like macros, and those all get saved out as a series of Python commands in ParaView. So a lot of integration there. Going the other way around, what if we get into like an HPC environment and we want to simply do ParaView-like things without running the GUI? There are 2 tools that come with ParaView. One is PV Python, So basically, this runs a Python shell and then lets you do paraview-like things, and it will pop up an image. We have to do certain things, like, see where it says show and render. There are some things that we don't have to do when we're using the GUI because they just happen auto-magically, but we have to do those with commands. And before this goes away, because this instance of paraview will be short-lived, notice that example, they save a screenshot at the end. PV batch is like PV Python, but it only works with input scripts. So this is what you want to use if you're running in a true HPC environment. Okay. And again, all of that is detailed in the paraview documents. Okay. So again, you're all experts in this now, of course. No, it's simply to know that if you get to that point, if your work is scaling out, again, paraview is going to grow with you. It's not going to let you down. Let's take a moment and talk about visualization at scale. So this is what this should all be truly about. But if, again, like I said, I've been doing this for 28 years. I would love to see more of our researchers doing, true scalable visualization. But the reality is most people say, oh, I'll just take these, I'll download these to my workstation. I'll just do a subset of the time steps. I will decimate my data. I haven't given up, but I know that human nature is such that I'm just happy that people are using visualization, either to help do their science or to help communicate about their science. And we remain open, trying to educate people on what they can do when their data is large, that they don't have to just look at a subset of the time steps or to decimate the data, but human nature is such that they will. So a practical definition I like to use for big scientific visualization is just what doesn't fit nicely, what doesn't work on your personal system. If you're willing to wait 30 seconds between rendering frames, then your laptop will probably be fine. But if you're not, you want something more interactive, then one of these things is for you. Again, what are the bottlenecks? What makes this so slow? It could be an issue of file storage, or it could be bandwidth. It could be the amount of memory. That's often what most people run into, is that we didn't really look at. There's things in paraview, memory inspector, so you can see how each time we add one of those filters to a pipeline, it is often copying the data. So you do have to be careful, because you can run into a data explosion, because you'll have multiple copies of essentially the same data set. Here, if I have a volume and then I clip it, I've got roughly half the data again. And if I make an isosurface, now I've got the same data in a different representation, but it's got all of the old versions of it. So I have to pay attention to my memory, or it'll actually run out, especially if you're running on a laptop. But it could be memory, it could be computation. We talked about things like transparency, like the difference between volume rendering a regular image grid versus just a regular structured grid, why that takes more time. Things like resolution. Okay, obviously, if you have a higher resolution image, that's more work that the graphics subsystem is going to have to do. Okay. Other challenges, this is getting better. There are more GPUs out there, but the darn AI people, machine learning people are squatting all over the GPUs. And that's actually fine, because a lot of visualization people now like to run ray tracing, and so they're happy to use CPU-only nodes. But again, finding those compelling things. Again, visualization is often a user-in-the-loop task, so it often requires at least in the early stages, and an interactive node, and that is not always available in your computing center. Again, interactivity changes the last mile problem, getting things across the network. And again, it's also hard because people have very capable machines. So what are the strategies when your data is too big to run on your laptop or your desktop system? We can go into what we call a distributed mode. These are in order of increasing complexity. Just in a client-server mode, we can parallelize the visualization. And then the coolest, kind of the Cadillac of this, is in situ visualization. Rather than doing visualization after the fact, we can actually build visualization into the simulation process. The nice thing is ParaView is your friend, your Swiss Army knife. It's going to support all of these. So technically what's happening when you're running ParaView on your laptop is you're loading up a client, a data server, and a render server. You don't think of it, you just think of it as a single application. You can pull the data server and render server off and then just have the client running locally. You can run your servers in parallel mode and so forth. So again, a lot of flexibility. So distributed visualization, this is an image from way back, but we can think of this pipeline, and anytime we can cut that pipeline between a server and a client side, and then that dictates what sorts of things that we need to transfer between the server and our client machine. So it might look like this if we're doing molecular visualization. So if we just want to bring down all the data, we would transfer over the actual raw data. If the data has been converted to some type of representation, we're sending over OpenGL commands. And then if we're sending over, if we want to do all the rendering on the server, we can just send over a series of images. Okay? And ParaView lets you do all of those. Okay. Which is most appropriate depends on what you're trying to do. I think one of the interesting things here is it was put to me as the span of human attention is often the threshold. You know, so it's that thing that takes long enough that you're not going to wait for it. You know, and so I've heard people put it like 30 to 60 seconds. Like, okay, that rendering is going to come out in 30 seconds. I'm not going to go get a coffee. I'm going to wait and see what the next thing is. You know, it's like, oh, it's going to take 2 minutes. Like, oh, hey, I'm going to go get a fresh cup of coffee. I'll come back when that's done. So, but often you lose focus on what you were trying to do. So those were interesting at one point, not so much anymore. So, but again, that's an easy way to build up more memory, take advantage of a GPU. Often you can just be running on a single bigger server, or in fact, that's what we're talking about there. If you then take multiple systems on the server side, you're getting into parallel visualization. And it should be said, one of the easiest things to do conceptually is to, you have a series of images that you're wanting to stream to your head-mounted display or to your desktop. If you get multiple systems, each working on successive images, you can do that. So you can basically, here it says time step 0, left eye, right eye, stereoscopic. Time step 1, left eye, right eye, so they can kind of go round robin. And so you could take 4 or 8 nodes, and that would be a way that you could keep your display fed while each one takes some amount of time. Again, these are some images that come from the ParaView tutorials. You can take your data set and you can partition it across multiple nodes. So here's just a 2D grid. That's great if each of the nodes or each of the subsets of data don't need any information about what's going on in the others. But that's often not the case. It needs to know what's happening in the neighbor nodes around the boundaries. So this is where they get into those ghost cells that are drawn in gray there. So So you don't get that linear speed up that you would be hoping for. You get something sublinear based on the number of nodes. People said, well, what if we just did some sort of random distribution? Depending on the scenario, that could be even worse, especially if you need all those ghost cells. You're basically duplicating all the data on each of the nodes. There are some beautiful things that people have done and do for, again, the really big data sets at the folks at the national labs do some amazing things. But you can take data and you can, again, this is what that would look like, taking our friend the head data set and putting it across 4 render nodes. Notice that in order to put that back together, we actually need to also have depth information, okay, so that we can know that the red stuff blocks the green stuff there in the second image there. So it's transfer of both image information and the depth map that comes along with that. And these can get amazingly complex. And ParaView and some of the associated libraries, ICE-T and stuff, beyond my experience. So you can do both spatial decomposition, and then you can do screen space decomposition, and these things can all come back together. Okay. And you can even do some type of load balancing. So again, if you were, say, drawing to a 2x2 tiled screen there and say the lower left, hey, we don't have as much, we don't need as many nodes. The upper left and lower right have more geometry. They need more things in there. So again, those again, gets very specific to a particular scenario, but it all supported in ParaView if you've got the need and the time to figure it out. The last scenario is what we call in situ visualization. So this is bringing, instead of saving your time steps out and visualizing after the fact, is to build your visualization into the simulation. Of course, so again, traditional run simulation, visualize later. For in situ, of course, we need to know how we want to visualize it, because once that data is gone, if we haven't visualized it in a way that's useful, the data is gone. The data is not saved out. But if we know, and often the case, think about the science you do and the scientists you might work with, they are often doing the same, very similar sorts of things year after year. So if they're doing visualizations, they know very much what they want to do, what sorts of representations, what sorts of viewpoints, color maps, et cetera, are very helpful. So we can actually take those designs, we can actually use ParaView to design what that looks like, and then Kitware makes a tool called Catalyst that lets us take that ParaView-like design, load it into our simulations, and so your simulation will run along, and at some point pause, and instead of writing out a data set, it writes out a series of images. And then we don't view, or we don't run ParaView later, we just simply run an image viewer. So the 2 pieces, Catalyst is the thing that brings ParaView to your simulation, and a cinema viewer or cinema database is really a set of images that we can view. So here's a number of examples, and they have this site, Cinema Science, that shows a number of these. Worth pulling up one since we're doing okay on time. There we go. And let's do a slightly smaller image size. And so then you can see that we can actually step through the time sequences. Now, we can't pick any arbitrary time because it was only saved at certain locations. Likewise, the rotational parameters are only set maybe every 30 degrees. Mouse at the same time. But it gives you a sense of, what might be gigabytes or terabytes of data is now being condensed down to an image. Have we lost something? Yeah, but we've probably gained a lot more in terms of being able to quickly look at that result instead of having to have reserved visualization nodes and load up all that data and go through it. We already had the data in memory while we were running the simulation. Why not go ahead and visualize it? So that's the notion behind in situ visualization. And by the way, here's some practical approaches, kind of going back to human nature, coming back to our laptops and our desktops. It is possible to work with a subset of the data. This often works well, especially if you then go and bring all of your data in. So again, that nuclear pasta was thousands of steps. We started by grabbing 100 or so, working through the visualization parameters before we rendered out everything. There also are ways to do a spatial subset of things, or you can look at, you can pull out the more interesting variables, leave the other variables behind, so you can transform the data, make a new set of VTK files that are smaller, and so on. On ParaView, there we can control what we call level of detail in terms of the number of polygons, the number of pixels that it would transfer. This can often help. And then finally, like we said, understanding your data, there's something called auto-apply. Every time you make a change in the pipeline, it propagates through. If you don't want that, turn that off, and so then you have to explicitly tell ParaView to execute the pipeline. Those camera control icons, it gives me heartburn to watch students, kind of flailing around, especially if they have a big data set with a low frame rate, because they'll overcorrect and then the thing will catch up and then it'll move here, move there. And if you're, say, trying to look down the x-axis or the y-axis, just hit that button and let the system catch up with you. But here's, again, if you're dealing with level of detail, you can really, go from something that's fairly, slightly noticeable to extremely noticeable. And again, images, if you can deal with a level of pixelization. Again, these levels of details, once you stop making changes, the system will catch up and it'll return you to the high resolution version. So it's not like you're going to be looking at that ugly skull the entire time. So there are preferences where you can come in and change those things. Questions on that? Okay. Wow. Well, we've skipped a few things, but we've more or less gotten it. So just a little bit of prognostication on the future of visualization. I was told in working with some HR people, we were all doing our strengths finders. I was told I was Janus. I was like, Janus, what's that? It's like, oh, it's the two-faced God who can look backwards and forward at the same time. So I see things, I guess it's fairly unique, see things as a continuum. So it's, I won't bore you too much, but where has scientific visualization been? So if we roll all the way back, actually, some of the first visualization was 1960s, but I came in about in the middle of that first generation there, where we had very limited scientific or sci-viz applications. We did have OpenGL, we did have VTK, but you had to make custom code for just about everything. So that Viz 5D, okay, we've got a bunch of researchers wanting to do weather simulation and visualization. Well, we got to write a custom code for that. And it got the job done. Things were standardized around silicon graphics hardware. We had a cave and an immersive desk. While that didn't have a lot of diversity of hardware platforms, the nice thing was people were really into sharing stuff, and stuff worked because people had basically identical systems. And I couldn't resist of showing this. Any old SGI people, users out there? Oh, John, great. This is what it would take to drive a single screen. It's a desk side on. It's like a big dorm refrigerator. And inside was a CPU board about yay big. My staff were mad at me because I won't let them throw it away because it's just, they've thrown away the rest of it, but we saved the boards to show. And then to actually do the graphics, the geometry engine, the raster manager, the display generator, each about a board that size. They all went side by side there. Of course, 2001, 2002, when NVIDIA first started doing their graphics things, a lot of SGI people went over there. You could get that down to a nice size computer graphics card. Now you get it basically to a chip on your phone that probably has close to the amount of processing power that did. But that's one of the things that's driving things forward. So that mass, again, that's just Moore's law there. So presently we've got the tool problem is fixed, so we don't have to go and write our own code. We have very flexible, multi-purpose applications. There's also lots of nice domain-specific things. So if you're into molecular simulation, you have things like VMD and Chimera. That's another thing I'll add in the last set of slides is some domain-specific things. If you're doing geospatial, you're probably doing QGIS, or you might be using Esri tools. Again, those things exist so that you don't have to write your own, unless you want to or need to. There's great displays, there's great hardware, there's emerging web standards. There's just one of hundreds of examples of visualizations that can be done online. We showed you things like spatial Sketchfab, et cetera, where you can put stuff online. So what does the future hold? You're going to see more of a convergence around real-time ray tracing. And the way it was best put to me is like, hey, I don't have to worry about having a separate pipeline for polygons and a separate pipeline for volumes and a separate pipeline for points. I can put all this together, and that's what people are particularly excited about for ray tracing, is I can have one algorithm that I can optimize, and it can handle any type of data that you can throw at it, instead of having a whole bunch of different formats. Remember we talked about at the very beginning, OpenGL being this collection of approximations. I think that things like what we saw with being able to put up models and worlds, will be able to do higher resolution, have less limitations. We didn't mention it, but we can't do volumes directly in there, so we had to turn everything into a set of polygons to put it into Sketchfab and spatial. At some point in the future, that's not going to be an issue anymore, so we can easily put up volumes. And we think those things are, nothing wrong. Images and movies are not going to go away, but I think they're going to be supplemented or maybe surpassed by a preference for interactive models, to go from more of a passive to an active type of interaction. So collaborating instead of just data journalism, looking at storytelling. And of course, AI is on everyone's mind. And there's 2 tracks, like at the Euroviz conference this fall. They talked about visualization to help out AI, but also AI to help out visualization. And so I resisted using generative AI until the very end, but AI thinks it can do a lot for sci-viz, and there's probably some good stuff in there. But in typical ChatGPT fashion, it gave us 8 things with sub-bullets and such. So it's going to save everything. And, kid you not, it can visualize nuclear pasta. So That was actually Adobe Firefly, and I was like, well, okay, we've got a long way to go. Now, it is possible to use generative AI to get ideas and stuff, but generally, those of us who do scientific visualization, no one is seriously worried about their jobs being replaced. But simply using those tools to help ideate on, oh, maybe this would be a better representation. Not that, that's just a joke. So, as I said at the very beginning, what's the best? Best biz software, the one you're most likely to use, the best platform, the one that fits with what you're currently doing, best presentation format, what are people willing to look at? What's the best biz display? We've kind of settled on this, the one that you've got with you everywhere. So we're most excited about things that we can find everything online. So anyway, hey, look at that. Right on. Thank you all. You've been good sports. Hope you got a sense. I know we didn't do a lot with peer review, but hopefully you've got a sense for visualization writ broad. Feel free to reach out to me if you have any questions. Oh yeah, and then there's that list of things, and I'll update it with, this has all the peer review information, but biz domain packages, biz design resources, et cetera, color map resources. We did skip over that, but all that's important stuff to be effective in your visualizations. So, thank you.